All right, in this module, we're going to start looking at transmission electron microscopy, or TEM. So before we do anything, I want to ask you a question. It's on the quiz. So we have talked about SEM, and we talked about how it's very common and easy to use. So with that in mind, why do you think we need TEM? So brainstorm some ideas, what you know or what you may not know about TEM, and see if you can come up with why we need TEM when we have something like SEM. So answer that, pause the video, come back, and we will discuss. All right, so let me give you some of the reasons I think that TEM is extremely useful, even though we have easier techniques like SEM. The first one is that SEM has very good resolution, but TEM is better. It is so good, in fact, that we are more or less able to see atoms. And I have that in quotes because technically we're not looking at the atoms, we're looking at the diffraction of a column of atoms, but we get the information so that more or less we're looking at atoms. Currently, when these slides were made, the resolution was 0.05 nanometers. So again, on the atomic scale, where we're able to, see these columns of atoms and determine structure and so forth in the material. Additionally, one of the big parts, one of the big features of TEM that makes it extremely useful is that we're able to study diffraction of nanoscaled regions. So we can do diffraction with something like XRD, but this allows us to look at the diffraction of very small regions, and so we can really pick our region that we want to look at. And so because of this, we call it selected area diffraction, or sometimes SAD or SAD. And so this is a very powerful technique that we can look at different regions. So we may have different phases or precipitates that have different crystal structures or different crystal orientations, and so we get a diffraction pattern from that. And so that's a very good use of TEM and something that we can't get with SEM. Also, TEM has a number of ways in which we can study composition, and we can some of these are techniques we can also do in SEM. So we talked about EDS. EELS is a new one, but these are things that some of these are things that we can do on SEM, but anytime we go have a higher resolution, we're able to use these techniques and really study composition at the atomic scale. And so that's what we can do with EDS and this process known as EELS, electron energy loss spectroscopy, allow us to get composition, but on the atomic scale. So EDS used to be fairly rare with TEM, but now it's much more common in what we can do. So other things that we can do with this technique that are difficult or impossible with something like SEM is that we can do atomic scale studies, but we can do it of actual processes. So something called in-situ. So we're examining it while the process is happening. So for example, we can look at cerium oxide or ceria. We can look at the surface at elevated temperature 750, and we can see what happens to the surface structure when we resistively heat it. So let me play you this video. And again, the resolution is so good, and we're able to get real-time examination of the surface with TEM, and we can kind of see that the surface structure changes with this elevated temperature. So we're able to examine this in real time. So again, this isn't going to be possible with something like SEM because we can't get down to this level of resolution with SEM. And this is all made possible with sort of more recent advances in our sample holders. So this allows us to heat up samples, put a potential flow current, change the temperature, also to be in a gas environment, similar to environmental SEM, and also liquid environments as well. So basically these advances in the holders of the specimens has facilitated some of these in situ studies. This is actually one that I was part of. I was actually there when they did this experiment. So this is a platinum electrode, and then we're kind of trying to mimic a lithium-ion battery. So we're depositing lithium dendrites. Dendrites are actually very detrimental to batteries. They can puncture holes in them, and so knowing kind of those, what happens there is a big issue. So we can basically look at lithium being deposited through an electrochemical reaction. So this is in a liquid cell. So let me go ahead and play you this video. Oop. There we go. So again, this is the electrode here, and then we're kind of cycling the potential, and that's changing whether lithium is deposited or dissolved. And so you can see the structure of that happen on this. So again, the power of kind of being able to see this in real time. All right. Again, this is one that I actually have a paper on, and this is the same in situ principle in a liquid cell again. So we have a wide array of things we can do. So this is a liquid containing platinum salt. And then the exposure to the actual electron beam reduces that salt into platinum particles, and you see their nucleation, and you also see their growth within this cell. And so if I just kind of play you the video here, you can see particles start to form and grow, and you see more particles form, and then you see their growth and coalescence as well. So again, you can see all of these features, and we're looking at very thin layers of liquid. So that's kind of, that's a pretty recent advancement to be able to visualize through a liquid, but it's a very thin liquid that's contained within a cell. And so you can see their growth and so forth in this cell. So these are some of the advantages to SEM. So SEM is definitely an easy technique, but TEM is very powerful because of the resolution and the compositional analysis, and also all these new techniques that we can do with it that kind of come out of all of those features.